Okay, we're going to get started in just a few minutes. Everyone has automatically been placed on mute until the end of the program when there will be time for questions. If you have a question that comes up during the presentation, please type it in the chat and I'll read it to Tim. This program will be recorded. Welcome to Astronomy 101. Timothy Campbell, a NASA Solar System Ambassador for Dearborn, will cover some astronomy basics such as objects of the night sky and how to find them, as well as some observing basics. Tim Campbell has always been interested in space. He was inspired watching the Apollo missions as a young child, but was really hooked when he saw the rings of Saturn through a telescope. While you can still find Tim looking through the telescopes, these days he wants to know how these things work. So cool, geeky science experiments are often added in for extra fun. Tim is a past president and active member of the Ford Amateur Astronomy Club in Michigan, and is also a planetarium operator and presenter at Henry Ford College. Tim does numerous outreach events and talks both under the night sky and indoors. Thank you, Tim, for presenting this program tonight, and thank you to all who are attending. With that, I'll give the stage to you.
All right, thank you. Let me just queue up my presentation here and take it into full screen mode. All right. Hey, thank you for having me. Yeah, as Henry mentioned, I am a NASA Solar System Ambassador. We don't get paid as Solar System Ambassadors. We are a community outreach initiative that NASA performs. So there are a handful of us in southeastern Michigan. I happen to be one of them. I'm also a member of the Ford Astronomy Club. I'm going to plug the Astronomy Club very briefly, only to mention that usually if people come to me at outreach events and they say, hey, I'm interested in getting a telescope, and I always tell them, don't get a telescope, go to an astronomy club, go to one of the outreach events where they have an observing night, look through other telescopes, ask those astronomers about their equipment. Every time somebody buys a telescope without going to one of these things and they don't really see what's out there, usually what happens is they end up with buyer's remorse. And they go, oh my gosh, for the same amount of money, I could have had that other thing that I would have liked so much better. So that's the only reason I mentioned that. The Ford Astronomy Club website, I have the URL there on the screen. And you'll see our calendar of events if you scroll down to the bottom of the main page. You do not have to be a member to attend a meeting. You do not have to be a member to come to an observing event. So we don't typically do observing events in the wintertime. So that caveated, they tend to start in the springtime. And with that, let's get started. So the stars that we see in the night sky, oops, go back to this. Why didn't the video start? There we go. The stars that we see in the night sky are actually always visible even during the daytime. But the trick is the light pollution from the sun basically is scattering blue light all over the sky. We can't see them. So as that light fades to dusky blue, you start to see a few of them. And as it gets darker and darker, you start to see more and more. If you've never been out of the city to a truly dark sky location, you're really missing out. You can see the hints of the Milky Way is starting to come into this video right now. And it's getting brighter and brighter as it does that. And in fact, this is what happens if you're at a truly dark sky site. You actually do see that with your naked eye, just like that. And it's breathtaking. A lot of people have gone through years and years and years of their lives and they've never seen this stuff. So it's out there. All right. So I wanted to take you through kind of the objects that are in the night sky to sort of introduce you to the kinds of things that there are. I'll talk about equipment a little bit. I'll talk about some book resources that are good. Feel free to ask questions anytime. Just punch them into chat. Henry will read them to me. I can take questions as I go, and I love answering questions. So to understand stars a little bit, you kind of have to know a little bit about how planets and stars are made. The idea is there is clouds of gas and dust in space. And for whatever reason, gravitational shock waves, whatever happens to occur to them, causes them to undergo collapse. They don't initially attract together based on just the force of gravity. So that was kind of a bit of a mystery how we know that the stars are made out of these gases. We just couldn't figure out why two particles of dust would have incredibly weak interaction through gravity. There's no reason that they would ever be drawn to each other. So why would this ever happen? So this is a little video clip that I'm going to show you with Dr. Don Pettit. He's on the space station when he's doing this experiment. And what he's taking is he's got a plastic bag, gallon-sized bag, and he's using whatever he has available. So he's thrown some salt crystals in the bag. And he's in essentially a microgravity environment. And what he notices is that these crystals stick to each other, right? So you can see it's sort of making this little chain. So he's mixing it up right now, but it's making this little chain of, he calls them floccules, clumps that clump together. He's a little suspicious because it's salt. And he's like, well, salt's highly electrolytic. He can kind of tell that this is probably static clinging that's causing these things to stick together. So he does the experiment again, but he does it with sugar. I'm not going to play the entire video. It's several minutes long. That sticks together too, just the way the salt is here. So he's thinking, well, maybe it has to do with the crystal structure of the sugar. So he does it again. This time he takes tea leaves and he grinds them up finely in his hand, and he puts those in. He's like, well, now I have organic matter that's not crystalline structure, not highly electrolytic, and it turns out that does it too. So when you have no interference from gravity, you know, where they're more strongly tugging at something else than they are to each other, the static cling wins, and these things want to stick together. So essentially what we now know is that static cling is basically what gets it going. Once you have enough stuff clinging together, sticking together, things start to accrete, and now gravity takes over. And so now things start to, you know, now you have a big enough thing, it weighs something and has some mass, and more stuff starts to stick to it. The pressure builds up and builds up and builds up. Now, when you take any gas and you squeeze it, it gets hot. That's how a heat pump works. It's how air conditioners actually work that way too. It's just, they're squeezing the gas on the outside of your house, and then they run it through a radiator to try and cool off what they got hot. Then when they bring it back inside your house, they decompress it very rapidly and it gets very cold. So squeezing gases gets them hot. So that's how a star works, is you're squeezing the gases, they get hot, and the core of the star, something like 15, 16 million degrees Kelvin. And now it's so hot that atoms of hydrogen, when they smash into each other, they normally would bounce off of each other, but now it's so hot that they smash into each other at such high velocities that they break. And it's that breaking that allows the bits that the atom is made out of to form a new heavier atom, and what it will form is called helium, right? So hydrogen fuses to helium, and then helium fuses to carbon and oxygen, and so on. Right now, our sun is just producing helium out of the hydrogen gas. So that's how these things get going. And then once it's hot enough, of course, then they start, you know, emitting light. Essentially, the sun is a ball of plasma. It's very hot. It's not on fire. Fire would require, you know, oxygen to burn. There is no oxygen. So that's how it's happening. Now, that's a nice theory, but it would help if we had some confirmation. So let me roll this little video clip, and hopefully this is working well for you. We're zooming in on a section of space called the Orion Nebula. It's actually visible right now. If you ran outside, I think it is still clear. I'll show you where this is in a later slide, how to find this. Now we're switching over to Hubble telescope imaging, and we're looking for something in this nebula, and we're going to zoom up toward the upper right a little bit and wait for it. It's coming up. And there it is. Okay, that little black thing. And you might be wondering, well, what the heck is that? Now, this nebula is really, really, really big, far bigger than our solar system, thousands of times bigger than our solar system. So what this is essentially a baby solar system that you're looking at. This is a baby star. It's called a protostar. That's the yellow-orange thing glowing in the center. And that black cloudy thing that you see going diagonally, that's what's called a protoplanetary disk. It's all the dust from the collapsing cloud. It's now swirling around the star, circling it. And as it circles, it starts to have things starting to accrete and clump and stick together. And those things that are clumping and sticking together will eventually become planets and asteroids and all sorts of other things. Now, once the star really gets going, it will start to pick up something called solar wind. And solar wind will literally blow the lightest particles of dust. It won't blow the heavy things out, but it will blow very faint pieces of dust out of that solar system, and it will start to clear out. At that point, it will no longer be possible for the star or the planets to really significantly grow. However much matter they managed to pick up while it was very dirty and dusty as it is now, is all they're going to get. And that's essentially how solar systems are born. And you might think, okay, well, we saw one once, but this is actually happening all over. This is the same nebula, by the way. So up here at the top, if you can see my mouse wiggling, that's where that first speck was that I showed you. But here's another one, and another one, and another one, and another one. Actually, the one at the bottom is kind of a better view because you're getting a little bit of a sort of a 45-degree top-down angle into it. So you can clearly see the star, and you can see the dust swirling all around it. So these are solar systems being born. This image that you see here was taken with the Hubble. Okay, so a little bit about stars. I'll point out a couple of them of significance. The first one I'm going to point out is the nearest star, the closest star to us. It's called Proxima Centauri. It was not known to exist until, I think, something like 1915. It's a little over 4 and almost a quarter light years away. Now, a light year is a measure of distance, not a measure of time. Don't be fooled with the fact that the term year is in the name. It's just shy of 6 trillion miles, a little over 5.9 trillion miles for 1 light year. So you can imagine 4 and a quarter light years is a little over 4 times 6 trillion miles away to get to this. And I'll give you some scale, some ideas about how to think of this by scale. Magnitude-wise, magnitude is a term astronomers use to talk about the brightness of something that we see. The Greeks had this idea that there were 6 magnitudes, numbered 1 through 6. 1 was the brightest thing that they could see in the sky, and 6 was the faintest thing that they could see in the sky. We've sort of perfected that a little bit in modern times, because now we have instruments far more sensitive than the human eye, and we realize that there are things dimmer than the human eye. The higher the number, oddly enough, the dimmer it is. So when the Greeks created the system, magnitude 1 was the brightest thing, and 6 was the, so 1 is better. Hey, we're number 1. 6 was the dimmest thing. So that meant that we had to create 7, 8, 9, 10. Things go on out to about roughly magnitude 22. And then after magnitude 22, we really don't see stuff anymore. Each difference in magnitude is approximately 2.5 times brighter. It's 2.51. If you want to know technically, it's the 5th root of 100 is how they come up with that number. And because they said, well, magnitude 6 should be 100 times fainter than magnitude 1. And you divide that, 5, 1 through 6, 5 differences, and that's how you come up with that. Okay, it's about 1/7 the diameter of our sun. So our sun, to give you some perspective, is 100. You can line up 109 planet Earths edge to edge in the width of the sun. 109 of them, and this thing is 1/7 of the diameter of our sun. So it's a lot bigger than the Earth. And then here's the scale thing that I wanted to give you. If you could imagine our sun being shrunk to the size of a basketball, Proxima Centauri is about 1.4 inches. That's the size of a foosball. If you play, on a foosball table, right? Virtual, soccer or whatever with the mechanical foosball table. That's a foosball. So imagine a foosball next to a basketball, and now you have a good comparison for the scale of our sun and Proxima Centauri. So it's a tiny little star, and it's not very bright, and it's the closest star, but it's so dim that we didn't even know it was there. By the way, you have to be in the southern hemisphere to even see this thing. You can't, it's not visible in northern hemisphere. The other thing about it is, if we took that same scale and we wanted to get the scale correct in terms of distance, and we have our basketball-sized sun here in Dearborn, Michigan, that little foosball needs to be someplace 4,500 miles away. Now, it turns out the Hawaiian Islands are 4,500 miles away. So you can imagine basketball here in Michigan, foosball in Hawaii, and absolutely nothing in the space in between other than bits of dust and things like that. So there's a lot of empty space in space. We launched the Voyager 1 and Voyager 2 in 1977. So they've been traveling through space for, I want to say, 45 years now. In my scale model, Voyager has gone only 2 of those 4,500 miles. in that 45 years. If you do the math, and if it were going in the correct direction, it is not, by the way, it's not heading in the direction of the star. But if it was going in the direction of that star, it would take 80,000 years to reach it. So that's just something to think about. So the next time somebody says, hey, maybe we were visited by little green men, just think about how long it takes to get to the nearest star. It's quite a daunting task. So here I've got a visual, our sun and Proxima Centauri once again. By solar mass, it's 1/8 of the mass of our sun. In other words, 1/8 of the material. Here's my fun question, which is, which one do you think lives longer? So our sun has been around for about 5 billion years. It has fuel to last about another 5 billion years before it starts to run out of fusible hydrogen. Proxima Centauri, however, sips through its fuel very, very, very slowly. Oh, also, our sun can't convect. So the fuel in the core of our star, the only place hot enough for nuclear fusion to occur, it has to already be in the core for it to fuse. The hydrogen that's farther out on our star is unable to get into the core. The atoms are so tightly packed, it might as well be cement. It's not cement, but I'm just trying to give you an idea of how tightly packed it is. And that's why it can't convect. But this star is smaller and lighter, and it does convect all the way through to the core. So when our star dies, it will only have gone through about 1/10 of 1% of all of the available hydrogen in the star. That's the amount that's available to fuse, and that will last 10 billion years. Proxima Centauri actually will do a pretty good job going through most of its fuel. It will last 4 trillion years. That's with a T. It will outlast our sun 400 times over, to give you an idea. So that's kind of a mind-blowing thing. The universe isn't that old, so none of these things would have died. No stars that small would have died yet. All right, so let's point out where this is in the night sky. Tonight, this probably would be, so you can see the south over here in this corner. This is actually meant for, this is probably done for, I'm going to say November. Orion would have been over here. Right now, Orion is more due south, maybe slightly to the southwest side. So if you go out of your house and look up, you should see 3 bright belt stars here. They'll be more spaced out if you're really outside, though. This is sort of wide angle lens, so everything's sort of scrunched in. You know, objects in mirror are farther away than you think. And if you look there, sort of here's the body of Orion the Hunter. And these stars, they call them the belt stars. He's holding a club and a shield, and he's fighting something. And then if you look down here, they call this the sword, these stars that sort of go up and down. And actually, if one of those stars there, if you look at it very carefully, in fact, grab a pair of binoculars if you have some and look at it, you'll notice it's not actually a pinpoint of light. It's this fuzzy patch of light. And that's because this is a nebula in space that is so bright that you can actually see it with your eyeballs. You don't actually need a telescope. Now, you're not going to get any detail unless you get a telescope or binoculars or something. But it is actually possible to see it. And that was the spot in the sky that you were looking. Look at these 3 stars here and follow them sort of to the left. And then we'll come to this star. And this star is Sirius. Sirius is the brightest star in the sky besides the sun, because the sun is technically a star. So I guess we could say the brightest star in the nighttime sky, because the sun is never up at night. And it is it's part of the constellation Canis Major, which means the big dog. You can sort of see the dog's head here. This would be like his dog tag, sort of body here, front legs, and down here are back legs, down at the bottom. Now, this time of the year, if you look out, it'll be a little more tilted over, slightly angling up. So it won't be so sideways like this. It's only 8.5 light years away, so that's still pretty close, but its magnitude, notice it's actually a negative number because, you know, you're trying to get to brighter than 1, right? And the Greeks decided that 1 was the brightest. And we said, no. After the Greeks had assigned brightnesses to things, and now that we can carefully measure, we actually realize that this is a lot brighter. So things actually get negative magnitudes to show that they're even brighter than 1 and brighter than 0. It's about twice the mass of our sun. Physically, in terms of size, it's not a whole lot bigger, but it has about double the mass. All right. Then there's the furthest object in the night sky that you can see. And this is a star named Rho Cassiopeia. Now, this is actually pretty spectacular. It's very, very rare. There are only 7 of these things known to exist. It's called a yellow hypergiant star. But what's amazing about it is it's 8,200 light years away. Our Milky Way galaxy is about 100,000 light years across. It is home to approximately 400 billion suns and a whole lot of planets. And yet, for 100,000 miles across, the most distant star we can see with the unaided eye, we're not talking about using telescopes yet, is only 8,200 light years away. So we're not even seeing 1/10 of the distance across our own galaxy before we can't see stars anymore. And we can only see this one because it is monstrously bright. I want to say it's to your eye, magnitude 4.1. Not a super bright star. To 6.2, it's variable. You can make this out if you're in a dark sky, but you would make this out even in as long as it's not, maybe an urban sky, you wouldn't see it. But if you're just out in the countryside, you would easily pick up a magnitude 4.1 star with your eyeball. It is 500,000 times more luminous than our sun. And that is why we're able to see it at that distance. In our basketball scale, it gets a diameter of 375 feet. So I did a presentation like this for Lincoln Park, and I used this is actually a satellite picture of their school, and there's their football field. And you can see that if next to a ordinary 10-inch diameter basketball, if you put this on the 50-yard line, it blows out the goalposts at the end of the field and crushes the spectator stands next to a basketball size representing our sun. So it's pretty massive. There is stars much more massive than that. This is a star named VY Canis Majoris. By the way, notice Canis Majoris is Canis Major. This is actually back, remember where we talked about Sirius, the brightest star in the sky? This is a different star, but it's in the same constellation. There's contenders for about 6 stars. We're not quite sure which of them are probably the biggest, but this is the one that I go with, that I think is probably the biggest. Here's an inset. There's our sun, and there's Canis Major. So our sun looks like nothing. It's a speck. It's a pixel next to this thing. It's a red hypergiant, 3,800 light years away, so it's much closer. And its magnitude is 6.9. So that is a little bit beyond what a typical person with decent eyesight can see. Maybe somebody who has spectacular eyesight might be able to make out 6.9, but 9.6, no way. Got to have a telescope. So you got to have a telescope to see this thing. But its surface diameter is over 1,400 times bigger than our sun. So with our 10-inch basketball scale, this has a diameter that's more than 1/5 of a mile. So here's back to the school again, right? So, we've taken over the entire football field. We've crushed their middle school completely, and half of the high school has been crushed as well. So this is a monstrously huge star. So they do actually exist. All right, now we're going to get into some deep sky objects. Before we get into deep sky objects, there's something that I want to sort of warn you about. Not warning as in you have something to be afraid of, but prepare you for some disappointment. People buy telescopes, and the boxes on these telescopes have gorgeous pictures on the box, right? Showing all these wonders of the night sky in gorgeous, stunning color. When you look through a telescope, this is not what you see. Very young children actually can see some color in objects. So we've had them look at objects and they've never seen them before. And we say, well, what colors do you think those are? And they nail it. Not every kid does, but quite a few of them do. But as you grow older, you lose that sensitivity to the color. So, the things I wish I knew when I was younger that I could have taken advantage of. But a little bit about how our eyeballs work. The retina of your eye has both rods and cones. Rods sense light. They're very sensitive to light, but they cannot detect color at all. Cones detect color, and there are actually typically, most people have 3 kinds of cones, and that's why we have sort of this red, green, blue thing going on. There is a small percentage of people who actually have 4 kinds of cones. It tends to only happen with women. Some people only have 2 kinds of cones, and some people only have 1, and that tends to only happen to men, and then they have some form of color blindness. So The problem with the cones is more light is required to saturate them before they activate and register that they see something. Whereas the rods, almost no light needs to hit them and they can see something. So we tend to see things through our telescopes because there's not a lot of light coming in, mostly with the rods. So it's mostly with the black and white that we see, and we tend to not get quite enough light for the cones to activate, except for maybe if you're young and have pretty good vision. So with that, here's an example of what you might see through a telescope in moderately light polluted skies. You can see I've got sort of a smudge in the middle of the screen, but I don't quite know what this smudge is. Well, I know what the smudge is, but if you've never seen this before, you have no idea what that smudge is. Let me put you in a darker night sky scenario, right? And now we're looking at the very same object. And what I've done is I've taken away some of the light pollution and improved the contrast on this, the very same object. And this is what you might see through a telescope. Now you'd want a telescope, fairly low power telescope, maybe 500 millimeter telescope. Don't go crazy and get something thousands of, because if you had a really big telescope with, I have a telescope that had a focal length nearly 3,000 millimeters. I would see just a tiny little piece of this. I needed a whole lot of telescopes to be able to see the whole thing. But a low power telescope is actually ideal, or binoculars is ideal. And this is about what you'd see, probably not quite this bright. Okay, if we want to see this in color, we got to use a camera and we've got to do some image processing on it. But if we do that and we stack all the images together and we use the software and we tell it to improve the contrast and darken the background and brighten the foreground and increase the color saturation, this is what we get. This is the Andromeda Galaxy. So this galaxy is, I want to say something like 160,000 light years across. It's not the nearest galaxy, but it is the nearest really big galaxy. Our galaxy has about 400 trillion suns. I'm sorry, 400 billion suns, I misspoke. This galaxy has about 1 trillion. So it's quite a bit bigger. By the way, it's on a collision course with us. And so years and years and years from now, not in our lifetimes or anybody we know, it will eventually crash into, our galaxies will crash together. When that happens, don't be afraid. Almost no stars or planets will hit any other stars and planets. When galaxies collide, remember I told you, basketball, 4,500 miles, foosball, and nothing else in the space in the middle. So imagine you're flying over the planet and you, in your spaceship, and you open the window and you toss out a couple of sports balls as you're flying over our planet. What do you suppose are the odds that the objects that you tossed out could hit the basketball in Dearborn or the foosball in Hawaii? And that's why I say they mostly just shuffle together and reblend and become a bigger galaxy. Now there's trillions of chances for one star to hit another star, so it might happen, maybe a few, but by and large, no, most things just sort of shuffle together and make a bigger galaxy without any spectacular explosions occurring. Okay, so let's talk about nebula. So I did mention those gas clouds that form the suns. That's what this is. So this is one of those gas clouds. It's star forming. You can actually see quite a few stars have formed in it. Here, these are the bright ones. There are doubtless many more hiding behind the dust that we can't see. So one of the things that the James Webb will do is it will allow us to see through the dust, because you can do that when you have infrared telescopes. Again, this one is this was taken by a member in my club. This is done by astrophotography. So he's got a telescope with a camera on the back of it. And he takes images for a couple of hours, and then he assembles them together and tells the computer to enhance the color. And this is what you see. Through binoculars, however, you'd see something that looks a lot like this, but in black and white. Mostly in black and white. Here's another one. This is called the Triffid Nebula. So again, these are where stars are born, like the Orion Nebula that I showed you earlier with the star forming going. These are more nebulas that are star forming. And lastly, the Eagle Nebula. Now I'm going to show you where all of these are in the sky. This is visible really only in July, August timeframe. This is a summer thing. So you can see the heart of the Milky Way going through here. And in that section, the first thing I showed you was this thing called the Lagoon Nebula. This is actually easy to spot if you're in reasonably dark skies with a pair of binoculars. You'll see a smudgy spot here. The Triffid Nebula is just a little bit above it. And then higher up still is the Eagle Nebula. up there. There are a lot of gaseous nebula in the band of the Milky Way because, of course, that's where most of the stuff is in there. To find this, there's an asterism called the Teapot. So the Teapot is not the name of a constellation. It's just an asterism. It's an interesting shape, and you'll see why. So these stars here form the pot. So there's the main part of the pot. There's the lid to the teapot. There's a handle to the teapot. And there's a pouring spout up there. The pouring spout, by the way, points directly at a spot right about here. You don't see anything. It's called Sagittarius A star. When you see it written, it's A with an asterisk next to it, but it's pronounced A star. That is the name of the supermassive black hole in the center of our Milky Way galaxy, and it's right there. And I'll tell you a story if I have time about how we found that. Okay, so this is a summertime thing to be able to locate. By the way, the teapot is properly in the constellation Sagittarius. You got to have an imagination to sort of see the shape you're meant to see with Sagittarius, which is sort of a centaur with a bow and an arrow. But the teapot is actually pretty easy to spot. Okay, let's talk about open clusters. So we talked about the stars being born in those stellar nurseries, and the emission nebula are the essentially the nurseries of the galaxy. It's where stars are born inside those nebula. Think of these as teenagers. They're no longer in the nursery, but they haven't quite moved out of the house. So these are all siblings. All of these stars were born in the same stellar nursery, roughly at the same time. The way we identify open clusters is in astronomy, we're able to take very precise measurements of these stars. We're able to figure out how far away they are. We're also, in a human lifetime, stars don't really seem to move. But we know that they actually do move, but it takes hundreds of years to notice a movement, maybe thousands of years before movements that are maybe only even a degree in the sky after thousands of years. So they don't move a lot, but they do move. And with really precise instruments, we're able to detect them moving just over a few decades. And so we can determine what direction they're going and how fast they're going that way. So the way we figure out that all of these stars in a cluster were born in the same nursery is they're all going roughly the same direction and roughly the same speed, and they're all roughly the same number of light years away from us. And when all of those things add up, we go, okay, they're probably they're family. These are siblings. So this cloud that you see is this is not the stellar nursery that they were born in. These stars were born far away, and they happen to be going through a piece of space that has a lot of gas and dust in it. So they're just lighting it up, but this is not where they were born. It's about 700 light years away, and this is the Pleiades. You can see this, by the way, out tonight. The way you find this is, remember those three stars that I talked about, the belt of Orion, the hunter? Instead of following them to the left, follow them to the right. And when you follow them to the right, you'll find a bright red star called, Aldebaran. We call it the red angry eye of Taurus the bull, but Aldebaran is the name of the star. And it's sort of a V shape, which is sort of his face, and it goes up and the bull's horns are up above that. But if you move a little bit to the right of that, you'll see this bright, very bright grouping of stars clumped together. This is probably the brightest open cluster in the sky. That's an obvious open cluster, and you don't need binoculars to see it. It'll just pop right out at you, and that's the Pleiades. This is a little farther away. So this is something like 7,000 light years, I want to say, instead of 700 light years. You do need a telescope to see it, but this is two globular clusters, open clusters side by side. And so they call it the double cluster. It's in a place in the sky halfway between Cassiopeia the queen and Perseus the hero who saves Andromeda in the Greek myth. And so halfway between those, you point a telescope to that spot in the sky and you see these two. And it helps to be a low power telescope. You'll notice this is the second time I'm emphasizing low power in telescopes. People sometimes want to find the biggest thing they can possibly get. That's great for certain types of objects in the sky. There's no best telescope. They all are better at some things and worse at other things. But this grouping is spread out far enough that if you had a really big, powerful, high focal length telescope, you wouldn't be able to see both of them. in the same field of view in the telescope. You could look at one, and then you have to point it over here to look at the other. But with a lower power telescope, you see both of them, and they're just gorgeous. All right, and here's one that this might be a little familiar to some of you. If I'd say raise your hand if you know how to find the Big Dipper in the sky. Unfortunately, I can't see you raise your hand, but this is the Big Dipper. It's pretty easy to find. It's the Big Dipper is what's called a circumpolar object in the sky, which means it goes around the pole. It never actually sets below the horizon. So we are 42 degrees north of the equator here in Michigan, and that means that the North Star in the sky is 42 degrees above the horizon, and none of these stars are more than 42 degrees away from the pole, which means that they never actually set below the horizon. These are up all day and all night, all year long. The Big Dipper, by the way, is not actually an official constellation. The real constellation is called Ursa Major, the Big Bear. If you come to the planetarium show, I show you the whole thing with a laser pointer. But we identified 55 stars. Only 8 of them are bright enough to be seen with the human eye. So here are the 8 that are bright enough to be seen, and I've circled them. And these are actually all part of an open cluster. But this open cluster is only about 80 light years away. Now remember, the first one I showed you was 700 light years away, and the second one was 7,000 light years away. Well, this is only 80 light years away. So it's not quite 10 times closer, but close, probably like 9 times closer. And so I've circled these things. And so they're so spread out across the sky that we are too close to this open cluster to notice them as a compact object, even though in fact they are by cosmic standards. So that's called the Ursa Major Moving Group. It's the nearest open cluster to us. Here's another one called the Owl Cluster, and you can kind of see the owl's eyes here, and you can sort of imagine, actually I'll just draw it in for you, sort of the wings, and this is how they get the idea of the owl. I don't know the ages of those of you who are participating tonight, but kind of lost on the younger kids. When I grew up, E.T. was all the rage. And so people said, hey, that kind of looks like E.T. Now, unfortunately, a lot of the younger kids will say, who's E.T.? So they kind of miss it. But anyway, it's also sometimes called the E.T. cluster. All right, so let's get into the next one. These are globular clusters, and these are some of my personal favorite objects to look at in the night sky through a telescope. The first time I saw one of these through a telescope, I was just blown away. And I was even more blown away when I found out what they actually were and why they were so cool. Everything I have shown you up to this point are objects that are inside the Milky Way galaxy. And so the Milky Way galaxy, remember I said it's a little over 100,000 light years across, and slowly rotating in space, right? Around this sort of bulged core where we have a supermassive black hole called Sagittarius A star. These objects are not inside the Milky Way. So while everything in the Milky Way is sort of swirling around very, very slowly, so it takes crazy amounts of time, millions of years to do a revolution, but while everything is swirling around, these things orbit beyond the reach of the spiral arms of the Milky Way galaxy. And some of them are going up and over. If this is the disk, some of them are sort of going up and over and around, and some of them are going this way, and some of them maybe are going the other way. And so they're going in all different directions. But they're very old. And this particular one, you can see it's about 25,000 light years away. So now we're starting to get out to some distance. So of course, you got to have a telescope to see it. And it helps to have a pretty fairly high magnification. You would see it in a low magnification telescope, but it'd be pretty small. So this is helps to have a little bit more magnification to be able to see this thing. But these objects are, I want to say there's about 250,000 suns in this thing. And it just looks like a ball. I sort of visualize those balls of fish in the ocean that swirl around. That's what these are. And they're all sort of orbiting each other. They're very old. They're about 12.5 billion years old. And here's the object again, but this time not taken by my friend Gordon in the Astronomy Club, this time taken with the Hubble. And so you're really getting a zoom in on the core, and you can see the crazy numbers of stars here. Most of them are yellow, and every so often you see a blue one. The reason, so blue stars don't usually last very long. They go through their fuel in a hurry because they're burning hotter. And so burning hotter means they're going through their fuel more rapidly. And so what we think is going on is these things are so dense that we think occasionally one of the suns smashes into another sun and forms one of these blue, brighter suns by giving it more mass. In the area of space that our sun lives, the density of stars is about 1 star in every 5 cubic light years of space. 1 star per 5 cubic light years on average. In this globular cluster, about 60,000 times as many stars in that same 5 cubic light year area of space. So it's quite crowded compared to what we're used to where we are. So that's one of them. Here's another one. They all look very similar. This one is M92. And here's just how to find them on the screen. So this tends to be something that you would find in, I would say, the springtime object. You can see this constellation here, this trapezoid here is Hercules, the hero from the epic myths. And between these 2 stars, about 2/3 of the way from this star to this star, almost right on the line is where you find this globular cluster. And then just up above it is the other one you saw. But wait, there's more. Here's another one, and another one, and another one, and another one, and another one. And so they're all over the place. And so here's why they're cool. Astronomers, we had no idea how big the Milky Way was. We didn't know where our sun lived. We figured there was a galaxy. We knew what galaxies looked like because we looked at not our own galaxy, but we looked at other galaxies. But when you're a blueberry that lives in the middle of a blueberry pancake and you look around, all you see is pancake batter. You kind of need to get up above the pancake and look down to figure out where your particular blueberry is. And we had no way to do that. So some clever astronomers realized that if we track these things over the decades, since they're not going around the disk like everything else, they're sort of going up and over in all different directions, that if we track their orbits, we could probably figure out more or less where is the center point that they all more or less agree on. And having done that, that is how we discovered that, well, they seem to be going around a center that's in the direction of the constellation Sagittarius. And remember, I showed you that teapot, and the spout sort of points at that little black dusty lane. And so they pointed their telescopes there, and of course they saw nothing because it was a black dusty lane and they couldn't see through it. So they grabbed an infrared telescope, and infrared can see through dust. And so that's one of the cool things about the new James Webb, is we will be able to look through dusty nebula, through the cores of galaxies and things like that with the James Webb, because it can see through dust. That's one of the great advantages of infrared. The wavelength is so long in infrared compared to the very tight wavelengths of visible light that when it hits a dust particle, the wave is far bigger than the dust particle, and the wave just wraps around the dust particle and just keeps right on going. And so that's why we're able to image with that. So this is how astronomers figured out where the center of the Milky Way was. Having done that, they figured out how big the Milky Way was, and they figured out that we're roughly, they used to say 25,000. I think now we're thinking it's more like 26, but about 26,000 light years away from our solar system and the center of the Milky Way galaxy. So about halfway from the middle to the outer reaches of the spiral arms. And that's where we live. And it's a pretty good spot to live. It's safe. It's not too crowded. We don't get bothered by too many other stars trying to smash into us and things like that. So we're in a good spot. All right. So I talked about galaxies. I talked about, well, I didn't quite get into galaxies yet, but I had to touch on it. We talked about how stars are born. We haven't talked about how stars die. And so that's what this is. This object is called the Ring Nebula. It's in Lyra the Harp, very close to the bright star Vega. And this is what happens when a low mass star about the mass of our sun runs out of fuel. Now, I don't have enough time to go through all the details of what a star goes through in its life as it's on its way to death. That would probably have to be a different talk. But when they do die, if they're not too massive, there's a point that gravity is trying to crush the star together, and the nuclear fusion is trying to blow the star apart. And so you get this stalemate where it's just happy and stable. But it's a stalemate, it's not a victory, because when you run out of fuel, and you're going to run out of fuel sometime, you no longer have a force trying to push the star apart, fighting the force of gravity. And so ultimately, gravity always wins. In the end, it's the one force that always wins. And so it's going to crush that star down, but as it does so, the outer shell of the star sort of gets blown off. And that's what you're seeing here. And so this red stuff is hydrogen gas that's glowing, it's ionized gas, and this sort of green-blue gas, that's oxygen. Oxygen gas being blown off, also being ionized. And this little fuzzy spot in the middle, that is the star. It's now called a white dwarf. It's no longer has nuclear fusion occurring in it. It is still quite hot, and it's so dense that it will be a long time before it ever gets cool. But eventually, white dwarfs become brown dwarfs, and brown dwarfs eventually become black dwarfs. The universe is not old enough to have any of these yet, but someday it would be cold enough that you could touch it with your hand and not get burned. But that will be probably beyond billions of years from now, hundreds of billions of years from now. I actually don't know the number, but on a huge scale of time before it is cold enough. Very dense, it will get very small when it does that. So an object like our sun would collapse down to an object maybe a little smaller than the Earth. Here's another one. This one is called the Dumbbell Nebula. And this time you see sort of this almost apple core shape of this red stuff. This is an image that I actually took using the telescope at that Lincoln Park High School. They have an observatory there, and I imaged this. And so there's the white dwarf in the center. You can see the red hydrogen gas again, and the blue-green, although the way I did the color processing on it's more blue than green, but that's oxygen gas. And here's another one. This is the Helix Nebula. And so these are very beautiful shapes, and some of them are swirly spirals and things. We hypothesize that because a lot of stars are doubles, that when one of the stars dies, but its partner is still out there, it drags gases around. And so you get some of these beautiful spirally shapes out of it. So that's why you come up with things like the helix caused by the gravitational tugging of other stars. Slightly more than half of the stars you see in the night sky are actually double stars, binary stars. It's a little less common to be just a single star, not quite half. All right. That's what happens when a smallish star dies, but what happens when a biggish star dies? And so here I've got an animation, and poof, it goes out into a spectacular amount of light. At that instant, the star is so bright that it outshines all the other stars in its host galaxy combined. So this is actually an animation of a star that went supernova in 1054 AD. Chinese astronomers actually documented the whole thing, but there were other cultures around the world that also noticed it and documented it as well. But the Chinese probably documented it the best. And so today, if you take a telescope and point it at that spot in the sky, you see something that looks like this. And so here's a very high resolution of it. It's called the Crab Nebula. It is in Taurus the Bull. So this is an object that you could see tonight with a decent telescope in a dark sky location. You'd follow those three stars to the right to that red angry eye of Taurus the Bull, Aldebaran, and then looking up, following the sort of the V shape. I think it's the horn that would be like on the left, all the way to the tip of the horn, and then just slightly to the right with your telescope, and you would find this. Now, this is Hubble resolution here. We're not going to see this with our backyard telescopes, but we will see, a little bit of this. We just won't get quite this spectacular amount of detail. And then I mentioned galaxies. So here's the Andromeda Galaxy again, our nearest neighbor. Distance is 2.2 million light years away. And in, I want to say something like 5 billion years, might be something like 4 billion years, it smashes into us. I have to go look that up again. But here is our Milky Way as an artist impression. And here's our sun, about halfway between the center of our galaxy and the outer edges of the disk. And here's our sun. And I mentioned that we only see less than 1/10 of the way around the galaxy with our naked eye. We have to use a telescope. So all the stars that you see in the nighttime sky really are just kind of in this area right in here. And if it's any farther than that, you got to grab a telescope to be able to see it. Here's an edge-on of our Milky Way, so you can image this across several nights. There is a, oh gosh, I'm not going to remember his name, and I don't want to slaughter it. But he is actually an astronomer here in Michigan, and he took what is essentially the highest resolution image of the Milky Way, going all around the world with cameras to be able to do it, put it together. Here's another one. This is a spiral galaxy, what we would call a face-on spiral galaxy called M101. By the way, I should mention these M letters. M stands for Messier. It's the fellow's name who discovered these objects. Charles Messier was a comet hunter who lived in the 1600s in Paris. And remember, the electric light has not yet been invented in the 1600s, and that means the middle of downtown Paris actually qualifies as a dark sky site. And so he's got his telescope, looking at these objects, and he's looking for comets. But in the early 1600s, telescopes really aren't very good. And so things are kind of fuzzy looking to him. And comets always they have this fuzzy thing they call the hair, the halo, or the coma. And when they get close enough to the sun, they'll form a tail. But the way you know you found a comet is you point your telescope at that spot in the sky. You get very excited when you see this. You plot exactly where it is in the sky relative to other stars that are nearby. And then you go back the next night and you look again, and you look again, and you look again. And as the days go on, you'll notice that the comet is moving across the sky. Well, when he does this, he discovers they are not moving. And so he is disappointed that he has been tricked into thinking something is a comet, but it's clearly not a comet. He finds many other objects that trick him, and he gets so tired of being tricked that he decides that he needs to make a catalog, a list of all the things that are not comets so that he will not get tricked again. And as he does this, he publishes this list to other astronomers who also send their submissions to him. He calls them comet imposters. One of his contemporaries calls them embarrassing objects. These objects are not worthy of your time. Today, now that we have pretty good telescopes, we look at this and we go, that looks pretty impressive to me, and it's a lot more impressive than a comet. So the Messier list, roughly 110 objects, M1 to M110, named for Charles Messier, the embarrassing objects that are comet imposters. And so that's why you see the letter M in the name. Here's another one called the Sombrero Galaxy. This is more of an edge-on galaxy instead of a face-on galaxy. You can see this big glow around it, very dramatic dust lanes going through it. And here's one taken by the Hubble. This one is a fascinating object because it's like a galaxy with a hole punched into the middle. And they don't know quite why this happened. There are some ideas behind it, but you can see sort of the bright core of the galaxy here, and where we should have spiral arms that attach all the way out, instead we have a donut. And so that's kind of a cool, interesting one. There is a project called Galaxy Zoo, where they managed to find galaxies that have every possible shape you can imagine, and they can spell every letter of the alphabet out of galaxies, or galaxy clusters, or colliding galaxies. Every letter of the alphabet. And so you can make greeting cards where you type in the name of the person that you want to say hi to, and they will spell out this message with galaxies. It's kind of a fun thing. It's called the Galaxy Zoo, I believe. You can look it up. Here's some interacting galaxies called the mice. This is a galaxy collision. So two galaxies get close to each other. You can see this galaxy was probably moving this way, and this galaxy got a little bit too close, and now it's starting to bend into its gravity. And as it does so, one of its spiral arms that's got a much weaker attraction to this gravity over here, because of how far away it is, sort of gets left behind. And so these stars that live, so by the way, the stuff that you see in galaxies, we can't make out individual stars normally. We can with really good telescopes, get left behind. So some of these stars actually get ejected from their host galaxies when the galaxies are merging. Kind of an interesting thing. I meant to ask everybody to bring a penny, because this is an interesting image that I'm going to show you. This is the original Hubble Deep Field, and this is probably my favorite image that I've ever seen in my life. You might notice this strange notchy thing going on here. what's really going on is when the Hubble was first put together, they got 4 cameras that are all put together, and the budget allowed them to buy. So this has got this nice big square here. That's a really big sensor, a big chip, very expensive. So the budget allowed them to buy 3, but they could not get 4. They did not have the money. So they put a little tiny sensor in here. Now, later they do a servicing mission to update the telescope. And when they do the servicing mission, it gets 4 big sensor cameras. So you'll see some images from Hubble that are square, but they call this the bat wing shape, because you can imagine, if this was a bat wing, like those stealth airplanes, this would be the front of it down in this lower corner, and this would be the back of it. And you get this sort of zigzag thing going on here. All right, so what's interesting about this image is this is 3,000 galaxies in an image. And here's how this came about. The Hubble is possibly the most famous telescope to date of all the famous telescopes. Now we have the Webb. We haven't gotten images back from the Webb yet. It'll be quite a few months before that happens. But the Hubble's been out there long enough that everybody sort of knows what this is. To get time on the Hubble is very competitive. You have to write a proposal, what you want to do, the science that you want to do, and you submit this, and your proposals are reviewed, and the most promising of them are granted some amount of time on the Hubble, windows of time. But there is a director of the Space Telescope, and one of the perks of being the director is that the director is allowed to have 10 days of telescope time on the Hubble that he does not have to justify. And so the director can look at anything they want. And so here's the director's idea. Everybody's looking at stuff out in space. The director says, what happens if we point to a spot in the sky that's completely black, has absolutely nothing in it, but we leave the camera open for a very, very long time? And so this was not a single 10-day long exposure. It was, in fact, many exposures, but it is 10 days worth of exposure at a small piece of sky. And after 10 days, they bring the data down and they look at it and they see this. Now, I can tell you that where you see this little spiky thing here, those diffraction spikes, that means that this is a star, and it's a star in our galaxy, our Milky Way galaxy. Here is another one, another star in our Milky Way galaxy. Up here at the very top edge is another one, but you can see I'm only finding like maybe 3 galaxies. I'm sorry, maybe 3 stars. Every other object you see in this image is in fact another galaxy, no matter how small. This little tiny speck here in front of my mouth that looks like a pixel.
Please. The library will close.
So that is another galaxy. So this is absolutely breathtaking when you think about it. There's a crazy number of them. Here's another one. This is the ultra deep field image, but let me take you to the last one. This is the ultra deep field, but it's been enhanced in 2014. We enhanced the data on it. This is 10,000 galaxies in this image and very few stars. Now you notice that I put a little dimension line here at the top that says it's 2.4 arc minutes across, and this is why I wish you had the penny. Everything you see in this image, if you take a penny and hold it up at arm's length, so it's the penny's way out here, everything you see in this image, you're probably thinking I'm going to tell you it fits in a piece of sky that hides behind the penny. Close, but not quite. Everything in this image hides in a piece of sky. If you squint, bring the penny in close to your face, look at Abraham Lincoln's eyeball on the penny. If you hold a penny at arm's length, the size of Abraham Lincoln's eyeball is 2.4 arc minutes in that scale. Everything in this image fits behind a piece of sky so tiny that it fits behind Abraham Lincoln's eyeball. That is absolutely mind-blowing to me. And they've done this in a few pieces of sky, and they realize they didn't just get lucky. This is everywhere. And so we now know there are hundreds of billions of galaxies out there. Each of them have hundreds of billions of stars, sometimes trillions of stars, and a whole lot of planets. So the universe is absolutely mind-boggling to appreciate the scale of it. All right.
Oh, Tim, I wanted to say that a couple of chats came in.
Yeah.
Someone was just saying what a nice program it is, but someone else is saying of the previous slide, it looks like a B-2 stealth bomber.
It does. Yep, and that's why we call it the Batwing. Yeah. So there's this quote by Carl Sagan. Those worlds in space are as countless as all the grains of sand on all the beaches of the Earth. So if you think about the Earth and how many beaches there are and how many grains of sand there are, he's not exaggerating. There are a lot of worlds in space. Each one of these stars probably has quite a few planets. We used to think we were getting lucky when we found the first exoplanet. Now there are thousands of them, and we're finding them all the time. All right, I did want to promise, I know we're running at the end of the program here. I wanted to talk about the basic telescope types, and I wanted to recommend a couple of books. The three main types of telescopes are refractors, reflectors, and catadioptric telescopes. Refractors use only glass lenses to focus light. They come in two flavors. Achromatic are inexpensive, a couple $100, $100 even. And there's a more expensive version called apochromatic. Typically, those will use at least 3 or more glass lens elements. And I'll tell you why. If I go on to the next image here. So here's an animation. You'll see light is going to enter the telescope from the right. These blue things are the lenses here. I think the animation is going to start. Do I have to click it? There we go. These blue things are the lenses. Now this first lens, if you think of like the end of it, like that's kind of like a little triangle shape there. And so that kind of works like a prism, and prisms split light, white light gets split into many colors. And so this second lens behind it is designed to try and correct some of that color separation that you get. So when you use this type of telescope, objects in the middle of the field of view that you see, they look pretty good. But objects out toward the edges of the field of view, you see some color fringing. Now, if you look at a star or a planet, you'll see a little bit of a blue fringe on one side, a little bit of a red fringe on the other side. And that's the separation caused by these lens elements. So the apochromatic add even more lens elements to do a much, much better job to create very good edge-to-edge sharpness. They also typically use exotic types of glass to make these things. Apochromatic refractors typically cost more than $1,000. I think I have rarely seen some that are less, but usually it's more than $1,000. But these achromatic reflectors, which is 2 elements, $100, $200, not too bad, and great for visual use, because usually you're just concerned about the thing in the middle of the telescope that you want to see, and who cares if there's a star at the edge of the field that has some color fringing. So not a big deal. However, the original telescopes, they had quite the problem with. They were trying to get them higher and higher and higher power, and they're making them longer and longer and longer, and the distortions were horrible. So Isaac Newton said, what if the light doesn't go through the glass? What if it bounces off of the glass instead? So reflectors use mirrors to focus the light. There are no lenses in the telescope. Now, you put these little eyepieces in the end, that has glass in it, but the main telescope itself has no glass. So to make a mirror, it actually is a piece of glass, but the light doesn't go through it. After they get the right curvature on it, they coat it with silver, but the silver coating is on the front of the glass. So typically, you want to go clean your bathroom mirror or something, you take a little bit of Windex, you wipe it, nobody worries about scratches. You do that to a telescope and you scratch and damage the silver coating because it's on the front. Remember, it's very important that the light does not go through the glass to avoid those optical issues. So that's what the reflector does. And so here's another animation showing you how this works. This is where you put your eyeball up here, and the light comes in the front. So the eyepiece is actually toward the front of the telescope, not the back of the telescope, as you might expect. Bounces off this mirror forward, and there's a little secondary thing here. They call this the secondary mirror. It's just a flat piece of glass on a 45-degree angle to bounce the light up into the eyepiece, and that's how you see it. So really, all the focusing is actually happening through this curved piece of mirror right here. And the last one is called Catadioptric. We call them CATs for short. All that means is this is a combination telescope. Some people call them compound scopes. It has both some lenses and some mirrors in the telescope at the same time. There are many variations on this design, but the most popular variation is called a Schmidt Cassegrain telescope. This is a design type of the telescope. It's not a brand name. And here's how this works. So the blue stuff, remember, blue stuff is glass. So that's actually a lens. And the yellow stuff, those are mirrors. So it comes through this really thick piece of glass. It's kind of a donut shape. So there's this center obstruction that you can't see through. Comes in, bounces off this mirror. This is also donut shaped, going around the center. The eyepiece goes back here at the back of the telescope. So light actually passes through this telescope 3 times. So all the way here to the first mirror, all the way back up to the front again, and then all the way into the back again before it gets to the eyepiece and or camera. And so that's how that telescope works. And to focus this telescope, you'll notice that I've got this sort of L-shaped thingy here. That's meant to be a sort of a tube surrounding yet another tube. This slides forward and backward. So this mirror actually slides forward and backward, and that's how the instrument is focused, by moving this large primary mirror. All right, last thing I wanted to point out, these are, actually this is the second to last thing I'm going to point out. 2 different books. Anytime anybody asks, what's a good book that you recommend I get to learn about astronomy? Terence Dickinson's book, Night Watch, is extremely popular, as is Brother Guy. Brother Guy is the director of the Vatican Observatory, but he's got a really good book called Turn Left at Orion. They tend to get recommended roughly equally. I happen to own Night Watch myself. I don't have Turn Left at Orion, which is shameful because I've actually met Brother Guy on more than one occasion. So you'd think I'd have his book and ask him to sign it. I suppose I should probably do that before I see him again. But they're both excellent, excellent books because you're not going to get lost in the jargon. They don't assume you're an expert. They take you through, assuming you know nothing. They teach you about telescope types, how to find things in the night sky by seasons of the year, where things are located, and so on. So they're excellent beginning resources. We often get asked to recommend telescopes themselves. Often we will recommend you start with a good pair of binoculars before you move to a telescope, just because the binoculars are a lot less expensive. You're not going to see some of those deep faint sky fuzzies in the sky, galaxies, and you will see some of the larger emission nebula through binoculars. But some of those objects, like I mentioned, like the planetary nebula, you're not going to see those in binoculars. You're going to need a telescope for that. And we get asked to recommend, who makes a good telescope. So first, you don't go to a big box store. You tend to go to these specialty stores that sell telescopes. As a NASA Solar System ambassador, I have to disclose NASA doesn't endorse products, so I can't give you brand recommendations. But NASA has something called the Rule of 3, which says that as long as I show you more than 3 choices, then I'm not really being biased. So in this case, I'm giving you 9 choices, and they're all pretty good. So all of these make, Celestron is sort of famous for their Schmidt Cassegrain telescopes I mentioned, as is Meade. Orion is more well known for their reflecting telescopes, as is Zoomel. Stellarview makes, and William Optics make really good refractors, as does Explore Scientific. Now, all of these companies make a little bit of everything, but some of them are more well known for some scopes than others. Again, I don't recommend you run out and buy a telescope. I recommend you come to an Astronomy Club meeting. Currently, those are happening through Zoom or WebEx. In fact, our club has one tomorrow night. Remember, I said you don't have to be a member. And then in the springtime, when we start doing the outdoor observing nights, you can look through various members' telescopes, ask them about it, find out what they like about it, ask them how much they paid for it, and you'll get a pretty good idea. Ask them what they would suggest that you get as a good starter telescope if you don't already have a telescope. If you do already have a telescope, you might be frustrated with it. It's not unusual for us to run into that. And so we offer these things called beginner's nights, where you bring your telescope out, where the club members have their telescope set up, and we show you how to, we take you through how to set up and use everything, and how to actually find stuff so that your telescope is making you happy with the purchase. That is all I have for the presentation. I apologize for running 10 minutes over. If there are any questions, do we have time for questions?
Sure. Thank you so much for this presentation, Tim, and thank you everyone who was attended tonight. Actually, a chat came in a minute or so ago. Someone said, wondering how long it will take for pictures from the Webb telescope to reach the Earth.
Oh, well, it's not about how long it takes to reach the Earth. It's about cooling off the Webb telescope. So the Webb telescope has a one of its sensors called MIRI needs to operate at, oh gosh, I want to say it's like 7 degrees above absolute zero or something like that. And so the problem with an infrared telescope is infrared is heat. And so the telescope was, on Earth, and we, where it's nice and warm, and you launch it into space, and the sun is beating on it, just like the sun beats on the Earth, and it gets hot. And so it's got these shields that always face the sun, so that the main part of the instrument is in the shadow, but it is so warm that it's going to take a while for the telescope to cool down. Now we're trying to get it to cool down very close to absolute zero. It needs to be pretty darn cold. It'll get pretty cold fairly quickly, but it won't get really cold for quite a while. And it does actually have some cooling systems to help it get cold, but we know that it will take the better part of 6 months before it's actually cold enough to do its main mission science. NASA is doing some alignment of the mirrors already, because they all had to be folded up and retracted to handle the shock of launching into space, because rockets tend to shake them quite violently. So the mirrors are all sort of moved into position, and they're being adjusted. They'll have to be oriented to make sure that they all point in exactly the same direction to focus light into the secondary mirror and then into the camera. So that's a process that's happening right now as we speak. Those mirrors are being aligned. It'll take a few months to get them all aligned. There will be some initial images that are done for press purposes. I thought that they told me that about a month after it gets to L2. So as a solar system ambassador, I get internal briefings on this stuff. I thought they said that about a month after it reaches L2, we're going to get some images, but those will really just be kind of the teasers, because the telescope isn't actually cold enough to do its real mission yet. So in about 6 months is when its real mission begins, because the telescope will finally be cold enough.
Oh, thank you. And if anyone has any other questions, you can unmute yourself, or you can type it in the chat. I actually see a couple more items came in the chat. Someone said, "Thank you, Tim. Hopefully bring my telescope when Ford Astronomy Club meets outdoors."
Yeah,
Another
absolutely.
person,
And again, I said, FordAstronomyClub.com, scroll all the way to the bottom of the main page. You'll see the calendar. We actually do keep that updated. We do indoor talks. Those are currently happening over Zoom. When we meet in person, we meet at Henry Ford College.
That's great. And let's see, someone said in the chat, they said, "How much time does it take to form a galaxy?"
Oh, galaxy formation is one of those things that is not super well understood. We don't actually have a lot of data on why they form. So an astronomer named Vera Rubin, so in the heyday of black hole discovery, Stephen Hawking and the like, everybody was going black hole crazy. And there's an astronomer, Vera Rubin, and Vera is a mother, and she's got kids. And she says, all these other astronomers are men, and they don't have to take care of kids. And so they can spend all of their hours doing all this research. And she says, and I've got all these duties that I have to do. I can't spend this kind of time. I'm never going to out-publish anyone. And so she says, I need to pick something that nobody really cares about anymore to study. So she decides to study galaxy rotations. And as she's studying galaxy rotations, I don't know the galaxy that she chose.
May I have your attention, please? The library will close in 15 minutes.
She discovers that the speed of the stars on one side of the galaxy versus the speed of the stars on the other side near the core are absolutely incredible. So incredible that there had to be something with an insane amount of mass there. And yet she can't see anything. And so she realizes that she's probably not just found a black hole, just any black hole. She has probably found an absolutely monstrous black hole, the mass of millions of suns, hundreds of millions of suns. And indeed she had. And so she beats all the other black hole people, because she found basically the best black hole there was, because she's studying boring old galaxies that none of the other astronomers care to study anymore. You're wondering why I'm telling you this. It's because then they said, well, what if let's study another galaxy and see what their galaxy curve is. And it turns out, so far, every galaxy that we study, and this is somewhat recent decades that we figured it out, every galaxy seems to have a supermassive black hole at the center of them. And we've also discovered a rather tight relationship between the size of the black hole and the size of the galaxy overall. Now, we don't quite know why. So right now, we're kind of in that taking in data, coming up with some guesses. Basically, science is not a body of knowledge. Science is a method of doing careful inquiry to see what we can learn. So they're studying these things. And with telescopes like the Webb that can see through the dust clouds into the galactic nucleus, we'll be able to study even more. But yeah, that's a really good question. I wish I knew the answer. We do know that all the active galaxies seem to have a lot of dark matter, and yet we do know that there are galaxies that don't have dark matter, and they're no longer doing star formation in them anymore. Globular clusters don't seem to have dark matter, and yet they almost seem like they're little mini galaxies out orbiting our galaxy. So we're sort of wondering, what role does the dark matter have in galaxy formation?
Thank you. Someone asked two questions. I'll go ahead and read both of them. One I think is a short answer. The other one's longer a little bit. Someone said, what is the link for the meeting tomorrow? And are some of the images or lights we really see stars that died and their light has taken years to reach us? Did that come through all right?
So yeah, so the softball question about the meeting tomorrow, the Astronomy Club meets, it's a 2-hour meeting roughly from 7 o'clock until 9 o'clock. The first hour of the club meeting is sort of club business, where they, reports, do we have money in the treasury? And yes, we do. And who went out observing and what did you see? So we do observing reports. And then after about usually 40 minutes or so, they usually take like a 20-minute break. What we did when we met in person, and everybody would socialize and have snacks. Now that we're meeting from home, usually the main presentation starts early. So the main presentation would always start at 8 o'clock. Now the main presentation usually starts at about 7:45, and it lasts about an hour. It's always the fourth Thursday of every month, except for November and December, because that would collide with Thanksgiving. So they do the first Thursday in December instead. But all the rest of the year, it's the fourth Thursday in the month. The hardball question was, are some of the lights that we see stars that died? Yeah. So looking through a telescope is kind of like a time machine where you look at the past but can't do anything about it. You can't touch it or do anything about it. We can't affect the past, but we see the past. So, light has a speed that was cleverly worked out by an astronomer named Ali Romer. Oddly enough, the problem they were trying to solve was to keep ships from crashing into reefs on the ocean and sinking, or missing their destinations and sailing right past. They were trying to solve this thing called the Longitude Problem. And it was Galileo who noticed that the moons of Jupiter have a very regular cycle. And it was Isaac Newton who was alive when they were trying to solve the longitude problem. And he remembered the work of Galileo. And so that was his idea, was to do the timings based on these moons that were orbiting. Remember, to find out how far north or south you are is easy. You take a sextant and you measure the angle of a star, like the North Star above the northern horizon, or the sun. What time the sun at midday, how high is it in the sky, and that'll give you your latitude. But to know your longitude, your east-westness, you kind of need to know what time it is. And the problem is in that day, they didn't have any clocks that reliably worked out on ships at sea, because they're pitching and rolling, and so you can't count on the pendulums to keep time. And so they thought of these moons of Jupiter. And they said, well, Io goes around Jupiter every 42.5 hours. We'll use that. So they made a table, all the dates and times when these moons should go around and start another orbit. And what they discovered was sometimes they're like 8 minutes early, sometimes they're 8 minutes late, sometimes they're on time. And so the craze in astronomy in those days was to try and figure out why moons speed up and slow down. And it was the Dutch astronomer Romer who realizes that no, every time they're early is when Earth is as close to Jupiter and our orbit around the sun as we get. And every time they're late is when we're as far away from Jupiter as we get. And when they're roughly on time is when we're somewhere in the middle. And he says, I think it's just taking longer for light to get across the solar system. And of course, they mocked him. But, you know, in mocking him, they have to show him up by proving that he's wrong. And when they went to prove that he was wrong, they ended up proving that he was right. And so it was accepted. Now, that's how we found out there is a speed of light for sure. There's a whole crazy thing that I can't go into after that. But so when you look at a star and it's, say, 10 light years away, you're seeing what that star used to look like 10 years ago. And when you look at a star 500 light years away, you're seeing that star, what it used to look like 500 years ago. Well, we now have survey telescopes that can look across the sky, and we see supernovas popping up all the time. Remember, there's crazy numbers of galaxies out there. And when a supernova pops up, you'll notice something that looks like a star in a galaxy that wasn't there the night before. And so you realize you found one of these supernovas. But when you find a supernova and it pops up in a galaxy, and let's say that galaxy is, let's say it's 10 million light years away. That supernova happened 10 million years ago. And so that star is gone, right? That star's been gone for, 9.9 million years and change, right? So because supernovas go really bright and then they start fading out over the next several months. And, by the time maybe 6 months to a year have gone by, you can't see them at all anymore. You know that there is now either a neutron star there or a pulsar. If it was big enough, maybe it became a black hole. But there's no star there for sure. And yet, for millions of years, you would have still continued to see light until that event has traveled through space and reaches your eye. So it's really fascinating.
Thank you. It
looks
like we just have one more question and a comment. Looks like the list is the last question. But someone also said, "Thank you. I learned a lot today." And then someone said, "Have you ever seen a donut galaxy?"
I have never seen a donut galaxy with my own eyeball through my telescope. I've seen many galaxies, just never one that hoax object that was imaged with the Hubble. That's really fascinating. I believe it's not unique. I think there are a few of them, but every so often you look out in the universe and you see something strange. And it's always exciting when you see something new that you've never seen before.
Well, it looks like that's all the questions. Thank you so much, Tim, for doing this tonight, and thanks everyone for attending.
Thank you for having me. It's been a pleasure. I love doing this stuff.
This has been an amazing program. People are saying thank you so much.
All right, thank you. Likewise. Glad I could do this.
All right, well, I guess in the meeting, thank you everyone, and have a good night.
All right. Thank you again, Henry. All right. Good night.
Thanks, Tim. Have a good night.
May I have your attention, please? The library will close in 5